think we're going to start. All right, can everyone see my screen and hear me? So can everyone hear me? All right. So a few things. This week is going to be the second to last class of, or the second to last class of like the session, I guess you could say. So yeah, just a heads up. So that means next week is going to be the last week, and even if it like might say on the website or something that we have another class on the 29th, there shouldn't be unless unless like the next class gets moved, but I don't think it's gonna happen. So most likely there will not be class on the 29th. It's just gonna be the 22nd, it'll be the last one, and that's it. All right, so that's just heads up. Anyway, this week I want to talk about number theory. This number theory is like the last major section or topic in math that is covered in most math competitions and that we haven't gone over yet. So there's quite a bit of lecture stuff to do today. So I don't know if we can get through all the problems. I guess the beginning part is just kind of stuff that I kind of talked about in previous classes and might be prior knowledge to some of you. So we start with factorials. I know I mentioned this in counting, where factorials are used to describe the ways to order n objects. And really the only thing you need to keep in mind about factorials for number theory problems is that they're often used in relation to divisibility in some way. And this is a bit easier to see in actual problems. So I won't say much more than that. Again, the bullet points kind of just say everything that I think is important about it. You can find all the notes in the classroom, they are posted. So we go to factors, and this is kind of like the basis of number theory, and it's that any number can be written as the product of prime factors, and each number has a unique prime factorization. And I think everyone should know what a prime number is. It's a number that is only divisible by one in itself. And so the prime factorization is just a product of all of these prime numbers to get this one number. And again, this will be kind of used to explore further topics. So that's all for that. Now we're talking about divisibility. And I guess this one, it's kind of universal tip. Just knowing divisibility rules for smaller, or like the first few numbers, is generally pretty helpful to any kind of problem, but number theory especially. So yeah, I made this table that kind of can be used to see if a number is divisible by the divisor 1 through 12. And you can look over them. I think that the rules for 1 through 6 are pretty well known, I believe. 7, I don't think there is any easily usable rule. The only one I can kind of think of, it's not a rule but a trick, and it's just that it also applies for 11 and 13. It's just that 1001 is equal to 7 times 11 times 13. So if you have a number greater than 1000, you can subtract a multiple of 1001 off of it and then divide by 7. which simplifies the number slightly. So it's not always going to be useful, but it can be used in some cases. Yeah, so the rules are all listed here. One thing I do want to point out is 11. You'll see this one being tested a lot. And it's just that the alternating sum and difference of digits is equal by 11. So I gave an example right below it. It's 254243 is equal by 11. And here you have what the alternating sum and difference of digits would be. So like you start at the left, and your first digit, you add that, then you subtract the next one, then you add the next one, subtract, and so on. And then, okay. Yeah, and then you just keep on doing that until you run out of digits. Then the final sum difference that you end up with, if it's divisible by 11, then the entire number is divisible by 11. And I don't know the proof of this off the top of my head, but the rule is indeed true, so you can use it. All right. So all of this is kind of just basic stuff, and it's all really helpful for what's next, which is the modulo operation. And I think this is among the most useful and characteristic operations in number theory. And usually it's denoted by mod, and it means the remainder when divided by. So for example, 5 mod 3 is equal to, and you'll notice that this equal symbol has 3 lines, and that is like the equal sign that you use for mod, because like the numbers themselves aren't equal, but the remainder when divided by 3 is the same. So that's why you have like a special equal sign. And so when you say something is 0 mod a number, that means that it's divisible by that number. The next, I think the most critical, I guess, theorem in just modulo, I guess, is Chinese remainder theorem. And it says that, Chinese remainder theorem says that for relatively prime integers, m and n, and this relatively prime point is very important. If we know that some number k mod m is equal to another number, and the same number mod n is equal to another number, then that means that there is a unique number such that this k mod m times n is equal to this number c. And this is kind of a very general explanation because a lot of variables, and also the variables a, b, and c are not related in any way, meaning that you can't actually figure out what the c is directly from what a and b are. You'd have to sort of guess and check. But the main reason why this Chinese remainder theorem is important is because it basically allows you to combine, I guess you would say, combine pieces of information into one larger, more useful piece of information, knowing that what you're doing is like rigorous in a sense. So while it may seem kind of obvious or I guess just intuitive, it's not at all like completely a trivial fact. So I can give an example. So let's say that we know some number mod 5 is equal to 3, and mod 11 is equal to 7 or something, right? So all the Chinese remainder theorem says is that it's going to be some unique modulo 50. It's going to be some unique number modulo 55. And this is actually going to be equal to 18 mod 55. And the way you get 18 is simply by trying every number that satisfies one of these two. So you start with all the numbers that are 7 mod 11, and then see if they also work for the previous condition. And what Chinese linear theorem says is that there's only going to be one such number that works for both of them. So as soon as you find one that works, you can stop. I know that that's your answer. And this becomes a lot more useful when you kind of use it to generalize to like more numbers. So what this says is that for any number, so not just 18, any number that satisfies these two also satisfies this third one. And I'm not entirely sure it goes both ways, but it definitely does go this one way. And I actually don't think I put any problems that use this directly, but it is still good to know. All right, I think we're gonna move on from that. If you have any questions, please do ask. It is kind of abstract right here, and I don't think I gave it too complicated an example. All right, so next we're gonna talk about digits, and this pertains more to like these combination problems where they ask you something about units digit, 10 digit, 100 digit, something like that. And the way you can deal with it, like in number theory, is by putting it in terms of modulo 10 or powers of 10. So like the units digit of some number is just that number mod 10. The last two digits is just gonna be that number mod 100 and so on. And I'll actually show a pretty cool problem that uses this idea and simplifies a lot. So we'll see. And next, when dealing with expressions with large exponents, so some number like to the nth power, and you want to find that modulo another number, if the two numbers are relatively prime, you can kind of just find a pattern in a sense. So, and the great example is 2. So if we have any number 2 and you say 2 to 107, what is this units digit? Right? It's not realistic to just calculate 2 to the 107. But what you can do is just find a pattern. And it's in that your units digits for 2 are 2, 4, and we just multiply by 2 each time. So 8, then 16, and 16th unit is 6. And then you just go back to 2 again, and this thing just repeats. So you can see that this has a period of 4. So that means that you can just take the exponent mod 4, and it's going to have the same units digit as that value. So that means 2 to the 107 has the same units digit as 2 cubed, or 8. And all right. So this actually it works for numbers that are not, when you're not dividing just by 10. So I think that this is pretty characteristic of mod, where if you have two numbers, let's say n and m, very creative, we know that this is just a property of mod. N times n mod some number k, for example, these are all variables, it's going to have like the same value as n mod k times m mod k. So essentially the mod value of the product of two numbers is just the product of each independent mod value. So like this idea is actually what makes something like the repeating pattern work. Instead of like taking like mod at the very end, you can take it at every single step, and you're not like doing anything wrong or changing your answer or anything like that. All right, so this is a pretty interesting tip to keep in mind. All right, so I think that's it for digits. Next is GCD LCM. yeah, I feel like these 3 points are actually all you need to know about them, where GCD of 2 numbers is the largest number that divides both of them. LCM of 2 numbers is the largest number that they both divide. And the product of the LCM and GCD of 2 numbers is equal to the product of the 2 numbers. So it's all written down. And I can give you an example. So like GCD 36 and let's say, I'm big, I don't want to deal with that. Let's say GCD of 12 and 15. And this can be equal to 3 because 3 is the largest number that divides both of them. And the LCM of 12 and 15 is going to be 60, as this is the smallest number that's divisible by both 15 and 12. And the product of these 2 numbers is 180, and 15 times 12 is also equal to 180. So from this example, you can kind of see each of the 3 properties I wrote. And I guess one thing I should mention for GCD is, while it's not like too often that you'll see something like that, if you're asked to find the greatest common divisor of 2 very large numbers, or not very large, but large enough to make it not immediately obvious what they're divisible by, like what their factorizations are. So if we have 2 large numbers, x and y, and you want to find this, we can use something called the Euclidean algorithm. And essentially what this says is that, so if we assume x is greater than y, this is just any loss without loss of generality. It doesn't really matter which one's larger. It says that the greatest common divisor of x and y is equal to greatest common divisor of x minus y and y. And the idea comes from, if this greatest common divisor divides both x and y, that means that it has to divide their difference as well. Because if it does not divide the difference, that means that x and y would have a different modulo value from each other. And that just means that x and y would not both be divisible by the GCD, which would be a contradiction. So then in this way, you can like repeatedly compare the 2 numbers and just take the difference and replace the larger one with the difference, until eventually you get to manageable numbers. And I guess if you keep doing it, eventually you'll get to some number in 1. Although I don't think it's completely necessary to go all the way down. But if you do, this, whatever this number left with next to 1, that's going to be the GCD. Actually, you're not going to be left with, you're going to be left with like 0. But yeah, it's really mainly just a tool to calculate it. You can kind of see from this example, you can change this to GCD of 12 and 3, and then you can change to like GCD of 9 and 3, or like 6 and 3, 3 and 3, and so on, 0 and 3. So then your GCD is 3. But it's pretty easy to tell that immediately from this step what the GCD is. So yeah, and that's really it for Euclidean algorithm. It's just a very useful tool in finding GCD when you're not completely sure about the factorizations. Right. So next we're going to talk about bases, and this concept is kind of like saying, what if the decimal system was not based on 10, but based on a different number. And in normal math, you could say we use base 10, which means that every digit has a place value corresponding to a power of 10. So like the units digit of a number corresponds to 10 to 0. The ones digit corresponds to, the tens digit corresponds to 10 to the 1. 100th digit corresponds to 10 squared, and so on. So like a number like 256 is equal to 2 times 10 squared plus 5 times 10 plus 6. And you can kind of see like each digit has a place value of some power of 10. And the idea of base is that when you change a number into a certain base, you just change this value from 10 to whatever that base value is. So in base, let's say base 3, and you have number 12 in base 3, this is equal to 1 times 3 plus 2. Or if we want more digits, we can put like another 2 here. And then you'd have 2 times 3 squared plus this. So you're essentially just replacing the 10 for each place with just this base value. And the base value is usually seen as a subscript at the end of the number. All right, and here's a more formal definition. I wrote it here, but it's a lot easier to understand just by thinking of place value. And the most important thing to remember about base is that each digit can only go up to 1 minus the value of the base. So you can never see like a digit 2 in base 2, because then this would like go over to the next place value. So similarly, how like the digits go from 0, 1, 2 all the way to 9 in base 10. In base 5, you only have the digits 0, 1, 2, 3, and 4. And if you can have bases higher than 10 as well. The most common base that's greater than 10 is hexadecimal. I wrote that here. And essentially the letters A to F represent the values 10 to 15. So if you see something like A and 3 in base 16, or hexadecimal as it's called, this would just mean this A means 10 times 16 plus 3. And these letters, if you do see them, that's what you mean. Yeah. Hexadecimal doesn't come up too often in these math problems. You'll see more like this different base stuff when you do computer science and stuff. And that's because computers don't use base 10 most of the time. That's kind of off topic. So that's really all I wrote on the note sheet, but there are still more things I want to talk about. I think they're a little bit more advanced. So I think that okay. So I want to talk about something called Euler's Totient function. And this is also pertaining to Modulo. And essentially, this guy Euler, he basically made a function. This is kind of simplification, but it's called the phi function. So this is supposedly the Greek letter phi, and I don't know what's called totient, but this like totient of a number is just equal to like the number of numbers less than n and relatively prime to n. Now alpha is like this, and the phi looks more like this. Yeah. But either way, regardless of what the Greek letter is, this is just a totient function, and immediately it doesn't really seem all that relevant. But like the weird or cool part, I guess you'd say, is that this is actually really useful in exponential problems, and we'll see that later. So the way you would calculate totient of a number is you take its prime factorization. So if its prime factorization is like 2 times 3 times 5 squared, so this number would be 150. And then you take, so if we have Totient of 150 in this case, it's equal to 150 times 1/2 times 2/3 times 4/5, which is equal to 40. And essentially, the reason why you can do this, where you multiply by, you say 1 minus 1 over each of its prime factors, is because of like the numbers less than that number, like including that number actually, half of them are divisible by 2, 1/3 of them are divisible by 3, and 1/5 of them are divisible by 5. And so any number that satisfies that cannot be relatively prime. So this is kind of like complementary counting. So these are all the numbers not divisible by 5, not divisible by 3, not divisible by 2. And so like they can't share any common factors. So like that's how you calculate Totient, and this general rule works for any number. And more importantly, like once you know how to calculate it, is that this other cool part formula that he had was that for any number like a, it doesn't, I don't think, oh, a relatively prime to another number. So let's say we have just a to the power of Totient of n is equal to 1 mod n. And yeah, I'm not going to prove that or anything, but I'm going to say that this is true for all n and a relatively prime to n. And there's no need to actually, well, I don't actually know how to prove it, because right off the top of my head at least, but just know that this is indeed true, and it is very useful. Because there is a cool corollary from here that's called Fermat's little theorem, that is a little useful in specific cases where this now pertains specifically to prime numbers. Any number relatively prime to that prime number to the power of the prime is equal to itself mod p. Or another way to write it is that a to p minus 1 is equal to 1 mod the prime. And this works because the Totient of any number or any prime number is equal to the prime number minus 1. And this is because from the definition of the Totient function, the only divisor of this prime number is itself. So like it just becomes that. So that's why Fermat's little theorem works, and it's just directly from Euler's Totient theorem you can get. So yeah, you can just keep that in mind. It does simplify problems a lot. Yeah. And no, I'm not going to mention. Okay, I think that's all for the things I want to talk about. All right, so now for the tips. Again, with number theory, as you'll see, a lot of it is just trying to simplify the problem and solving smaller problems and putting it together to solve like a bigger problem. So yeah, here are the tips. I'm not going to read them. You can see them in the notes. I don't think they're particularly useful. They're kind of broad, and these are just to see when we actually do the problems. All right, so I think we start from this one. How many positive integers n does the sum from 1 through n evenly divide 6n? This one is kind of just like a basic factor. Just basically test your factoring, I guess, or just how factors work. That's really all it is. So like the sum is equal to n times n plus 1 over 2. And we know that it has to divide 6n. So then you can kind of see that since they each have a factor of n, we can kind of ignore it. And so that means this n plus 1 over 2 must divide 6. So then n plus 1 must like divide 12. All right, and now all I have to do is factor 12. So 12 is 2 squared times 3. So its factors are 1, 2, 3, 4, 6, and 12. And now you can just subtract 1 to get all the possible values of n. However, since it does say how many positive integers n, 0 does not work since it's not positive. So then there are 5 values here, 1, 2, 3, 5, and 11 that work. So there are just 5 integers. So this one was kind of this is just super basic. I put it in here just so I guess you can just warm up to how like just a logical process for working like with the evenly divided stuff. All right, the next this one is let k equals 2008 squared plus 2 2008. What's the unit digit of k squared plus 2 to the k? This one is tied directly to the unit digit stuff that I talked about earlier. So essentially, unit digit is just going to be that number mod 10. And since we have a plus sign, we can just kind of split k up first into just 2008 squared and 2 2008, and we can address both sides separately. And now if we look at this final, like what we're asked for, you can also kind of split it up into k squared and 2 to the k. Since you're just adding them, you can find the unit digit separately and just add them to get the final unit digit. All right. So from there, we can also see that what we need to know is what is k's unit digit for one, and we also need to know what's k mod 4. And I said k mod 4 because earlier we saw that there's 2 cycles in a period of 4. So that's why the mod 4 matters here. And now we can accomplish both things by looking at what k is. All right, so first 2008 squared, this mod 10 is just equal to 2008 mod 10 squared. And this is from this thing I wrote here earlier. So using that, you can see that this is just 8 mod 10 squared, or 64. So and that just means it's 4 mod 10. All right, that's just half of it. So next half is 2 to 2008. We know that 2008 is 0 mod 4. It's easy to see it's divisible by 4, so that's why. And that means that it's going to correspond to 2 to the 4th, or 16. So what that means is that this unit has to be 6. So yeah. And then you can simply just add them because you know the last digit here is 6, last digit here is 4, the last digit of k must be 0. All right. There's really nothing that can go on in the adding process that like affects unit digit in any way. I think that's pretty logical. So then that means that like unit digit of k itself, so k mod 10 is just equal to 0. So what that means is that this k squared term is just 0. You don't really have to like mind it at all. All right. So now we have 2 to the k, and from how k is written, it's pretty clear that k is divisible by 4. 2 to 2008 is a very large power of 2, so it's divisible by 4. 2008 itself is divisible by 4, so it's also divisible by 4, like the square. So since both like the two things that you're adding are both divisible by 4, then like the entire sum is also divisible by 4. All right, so then we can use the same thing we did for 2 to 2008 earlier for 2 to the k here. And so that means that its unit is also 6. And since k squared unit is 0, then that's all we're left with. So that's it. It's just 6. All right, so I guess as this problem was an example more of just like working like from this, I guess, this big like combination of stuff, you could say, and just splitting it into parts and solving and considering each part individually, then putting them together until you get the solution. And that's all there is to it, right? So yeah, you shouldn't be intimidated by any large numbers. Just like if you just methodically kind of break it down, it just works out. Yeah. All right, so next we have a great example of this, which is what is the hundredths digit of 2011 to the 2011? And big numbers, right? And also the hundredths digit is kind of a pain because that means that you have to consider more more digits than you would for a units digit problem. And so the first thing you should do is immediately recognize that it should have the same hundredths digit as 11 to 2011. And this is because 2000 is divisible by 1000. So like since finding hundredths digit is equal to like mod 1000, or like the last two digits can be found using mod 1000, you're essentially taking this entire product mod 1000, and you can do it for each individual 2011. So that just changes everything to 11. All right, so that's like the first step. The next, we can actually use this cool thing called Euler's Totient Theorem. And it's just that since we are finding the hundredths digit, that means we want to take this total thing mod 1000. And the totient of 1000 is equal to 1000 times 1/2 times a 4/5, which is equal to 400. So what that says is that 11 to the 400 is equal to 1 mod 1000. And since well 2011 is greater than 400, we can take that mod 400 to get an equivalent value. So then this just becomes 11 to the 11 mod 1000. Right? This is because 2000 is divisible by 400, so then we can like kind of remove it, and that's just what we're left with. All right, and from here, there are a few ways you can approach it. This actually isn't very hard to just bash out from here. You can probably just keep on multiplying 11, 11, and then once you get to like something with more than 3 digits, you can just take the mod 1000 and keep going 11 times until you get the answer. That shouldn't actually be too time consuming, and it works. So if you are like, I don't know, if you don't want to do any more like simplifying or anything like that and just straight up solving, this is completely viable. I just want to get that out of the way. But I think that a more elegant solution is to use the binomial theorem. And I don't know if I talked about this earlier. I probably should have. But the binomial theorem kind of says that if you have a binomial, so something x plus y to some power n, it's equal to like x to the, all right, so I think I'll write it in sigma notation since that's kind of standard. It's equal to the sum from 0 to n, make it k, of like x to the k times y to the n minus k times n choose k. And it's kind of complicated, but it kind of just says that you can find you can find any individual term given the x and y exponents, at least of this expanded and simplified product. So an example would be if you have x plus 1 to the third, it's equal to, if you do calculate it, x cubed plus 3x squared plus 3x plus 1. All right. And usually when you have a plus 1 term, it makes it a lot easier, since now you only have powers of x and the exponent choose number. 3 choose 3 is equal to 1. That's coefficient here. 3 choose 1 is equal to 3. 3 choose 2 equals to 3. 3 choose 3, or 3 choose 3, or 3 choose 0 are both equal to 1. So you can see that the coefficients are always going to resemble that of a combination. And we talked about this. We talked about like what this symbol means last class. And I do want to mention exactly why this works. And it's because if we expand out, so if we go back to our x plus y example, n times, and let's say there are n of these binomials, to get a term with x coefficient of k, you're essentially like, when you explain it out, you're choosing one value from each of these parentheses to multiply together to get your final, or to get a single term, essentially. So like it's kind of like foiling with just a lot of parentheses. And each time, since you're multiplying binomials, you can only choose one of the terms inside each parentheses. And since there are n of the total parentheses or binomials you can choose from, and you need to choose k values or k parentheses in which you take an x from, there are going to be n choose k different ways you can choose k number of x's. So this would just be n choose k as the coefficient of your x to the k term. And since you have k x's, then you have to have n minus k y's, because the total like degree of your term has to equal to n. All right, so this is why you'll see some combinatorial coefficient inside the product. All right, and again, this is easily verifiable. You can just expand out like x plus 1 to higher powers by yourself if you are interested. This how it works. What is the answer to the exponent question? The exponent question, I'm assuming you mean 2000. I'm assuming you mean this one right here. The answer is 6. I guess that's really the only one I talk about with exponents. Let's talk about this one, which you haven't finished yet, by the way. So yeah, back to where binomial theorem. I hope that was a decent explanation of how it works, and the way you can apply it here is, and you'll actually see that this works for a lot of ones where you're taking a mod 1000, and we're taking a mod 1000 and you have some large exponents, and it's that 11 is equal to 10 plus 1. I don't think we can argue that, right? So then we can just write that as 10 plus 1 to 11. And these are obviously equivalent. But now the cool part of a binomial theorem is that if you notice, each of these like terms have like a different power of x, right? And in this case, x equals to 10. So if we do write it out, I'm not going to expand that like all of it, but it's going to look like 10 to 11 plus like 11 choose 1 times 10 to the 10th times 1 to 1, and any power of 1 is equal to 1, so we can just ignore it from now on. And then it looks something like this, right? And so eventually we'll get to like plus 1. And the reason why this is so useful when we're taking a mod of a power of 10 is because each of these terms are just equal to 0 mod 1000, because the exponent of the 10 is a lot larger than 3. So we can effectively ignore all of these terms until we get down to a term with a small enough power of 10. And there are only going to be 3 of them. And so if we have more room on the side, these three terms are going to be like 10 squared times 11 choose 2 plus 10 times 11 choose 1 plus, well, 10 to 0 times 11 choose 0, where this is equal to 1. And you'll note that any term higher, so like the next term is 10 cubed times 11 choose 3. This is obviously 0 mod 1000. So that's why we can ignore all the terms before this. And then this is very easy calculations from here. So this is equal to 5500. This is equal to 110. This is equal to 1. So when you add them, you'll see that like the final mod 1000 result is just 611. And since we're only finding the hundredths digit, it's going to be equal to 6. So yeah, that's how you could solve this one using minimum theorem. But again, this is kind of unnecessary because this number itself is small enough to be just bashed out. But yeah, this is the answer to the problem. It doesn't really matter how you get to it as long as you get the right answer. All right, so next we go to this one. This is the base problem, and I hope you can show how you can approach most base problems. I don't know how good of an example it is of that, but essentially in base 10, the number 2013 ends in digit 3. In base 9, it ends in 6. How many positive integers are there such that 2013 ends in digit 3 in that base?
4.
And so for base to end in a digit 3, it's essentially saying that this number 2013 mod the base is equal to 3. Now, why do we say this? This is because similarly how to like 2013 mod 10 is equal to 3, and that's the unit digit. We can write any number like in the base as a sum of the coefficients. Like the coefficients are a1, b to the, let's say cubed. Let's say it has 4 digits. Like this is just arbitrary number, right? So like every single other like term when we expand out its place values is divisible by like b. So just only that number that's at the very end is not multiplied by the b. So when you do take a mod of the base, that's what you're left with. And I guess in a lot of problems involving base, so sometimes it's not going to just be about usage and stuff. This is how you would handle it. You would just use algebra. So you can just convert any, like the way you convert any number in base to a base, from an arbitrary base to a base 10 is just by expanding out its place values and just calculating that total sum. But that's not relevant for this problem. But either way, I hope that you can see that all this means is that 2013 mod b is equal to 3. All right, so then once you have that, it's kind of simple. This just means that 2010 is divisible by b, right? And you can see when you subtract 3 by, so subtract 3 on each side, you'll get 0 in 2010. That's why we have that. All right, so from there, 2010 can be factored as like 2 times 3 times 5 times 67. And so that means that, well, b has to be some factor of 2010, right? And here's I'm not sure if I talked about this either, but you can quickly find the number of factors of a number by just their prime factorization. And you can do this by just adding 1 to each of the exponents and multiplying. So the exponents of each of these prime factors is 1. So it's just like our total number of factors is just 2 times 2 times 2 times 2, or 16. And you can think of this as like, say you're constructing a factor of the number. You can either have one factor of 2 or 0 factors of 2. You have 1 factor of 3 or 0 factors of 3 in it. 1 factor of 5, 0 factors of 5, and so on. So you can have like any number of like the 2's in your factorization. And so that means that you can just add 1 for like the 0 case for each of the exponents. So when you multiply, you get 16. However, we know that 1, 2, and 3 all cannot be equal to b, because this digit 3 is like in the number. So the base has to be larger than that digit. And that is very important to catch. So then you have to subtract 3 and get 13 as the answer. Yeah, I guess the emphasis here is that be careful with whether or not the base is valid. Other than that, changing the base problem from just in bases to like a completely different kind of column. All right. This problem, yeah, we're gonna skip it. If you want to look at it, I guess you can look it up. It didn't exactly load correctly. So we'll go to the next one, which is an integer n is selected at random in this range with probability that n to the 16th is divisible by, oh sorry, n to the 16th is 1 mod 5. And this should immediately remind you of Euler's Totient theorem, or in a sense Fermat's little theorem, since 5 is prime, where any number to the 4th is equal to 1 mod 5. This is just a direct application of that theorem, so there's really no work up to here. And from integer n is n to the 16th. Obviously, n to the 16th is some number n to the 4th power. So this equals n to the 16th. So this is clearly also equal to 1 mod 5, under the condition that n is relatively prime to 5. Because if m is not relatively prime to 5, this number is going to be equal to 0, because they have to be divisible by 5. However, that means that for all numbers not divisible by 5, it's equal to 1. And now that kind of just gives you your answer. N can be in this range of 1 through 2020. And note that this is, multiple of 5. There are 2020 numbers in this range. So 4/5 of them are not going to be divisible by 5. So that's just it. So essentially, for like 4 out of every 5 numbers is not divisible by 5. So in this range, 4/5 is a probability that like the integer you select is not going to be 0 mod 5. It's going to be 1 mod 5. All right. So this is a super simple problem once you just simplify it a bit, I guess, or just see that it's just some kind of like setup for a trick. All right. So next we have this one. This is a factorial problem, and it's not very relevant to factorials, but the number 21 factorial is equal to a very large number, and it has a very large number of divisors. And one of them was chosen at random was the probability that is off. So if you don't recall, probability is just number of successful outcomes over total outcomes. And essentially, what you cannot do is count every single one of the odd factors, because this number has just so many factors. You can't just list them out by hand. You have to find some better way. And essentially, what you should do is examine what's the power of 2 in the factorization of this number. And if you don't see right away why that's important, you should see later on. So to like find that, you can just say that this is 10. Yeah, this should be equal to 18. There should be like 18 factors of 2 in this entire factorial. You can verify this by just like listing out the numbers 20, 19, 18, and so on, and counting the number of factors of 2 you'd have. Another way you could do this is just by like finding the sum of this, where this is a floor function. I'm not going to go over why this works, but just know that it does. And I guess if you can figure it out by yourself, that'd be cool. If not, I'm sure this is available online as well. But essentially, no matter what way you do it, as long as you get 18, it should be okay. And then what's more important here is just why do we need to know this? And the idea comes from, again, if we go back to like the whole counting the number of factors here. If you think about, like, let's say you're constructing a factor of this number, you're going to have, like, if we split up factors of 2 and 3, 5, 7, etc., there are going to be a lot of them, right? Each one of them are independent from each other, and from this value of 2, we have can be any number from 0 through 18, and the same applies for every other number here, but that's not relevant to whether the number is even or odd. Only 2 is. And so the number of factors that are odd are going to be just the ones where this exponent of 2 we choose is 0. And it's going to be even if we choose any of the other numbers 1 through 18. So this is just one number out of 19. So the probability is just 1/19 that you get 0, and that's it. And you think about why this works, and it's because the number of divisors that you have with a power of like 2 to 0 must be the same as the number with 2 to 1 and 2 to 2 and so on, because there's a fixed number of divisors in this section over here that's not relevant at all to your factors of 2. So like each of the values of the factors of 2 has to have the same number of divisors like in there. So that's why you can just simply compare it to itself and not consider anything else. All right, so that's the concept I want to emphasize here. So we go on to this one, and I like this problem because this combines geometric sums, infinite geometric series with bases. So, and it also tells you how you deal with things after decimal point in bases. All right, so you see the problem for some integer k, this repeating base k representation of 7/51 is equal to this. What is k? So similar to how in base 10, if you have 0.1, this is equal to 1/10, right? 0.12 is equal to 1/10 plus 2/100. So the same system works with other bases. And what I mean by that is that like this expression in base k is going to be equal to 2 times 1/k plus 3 times 1/k squared plus 2 times 1/k cubed plus and so on. And similar to like repeating decimals with I guess in base 10 and base k, you can also like see them as a geometric series. And here there are clearly 2 alternating geometric series, one where the coefficients are 2, one where the coefficient is 3. So I'm still right, it's like 2 times like 1/k over 1 minus 1/k squared plus 3 times 1/k squared over 1 minus 1/k squared. And you can simplify this down. This becomes let me think. Just this. And I just can just use algebra bash and that'd be it. So sorry, it'd be 3 here. Maybe it's not working. It would just be 3 over k squared minus 1. And this whole thing is equal to 7 over 51. All right. So eventually you're just gonna be left with a simple expression for k, and you can solve this. And I won't do that right now, but it's just a quadratic equation. So if you do it on your own, it should be pretty easy. You'll get that k equals to 16 is your only solution. If you plug it back in, this is 32 over 255. Sorry, 35 over 255, which does simplify to 7 over 51. All right. And so what I want to get from this problem is that you combine number theory with something that doesn't seem super related to it, and like you can still get a problem. So it's good to be familiar with like all the topics and how to work with them. All right. We won't really have time to do the other 2 problems. So I kind of said like what I wanted to about number theory. I also said like what I wanted to say about logistics at the beginning of class. This is going to be second to last class, and yeah, next class is going to be last class. So yeah, if you don't have any questions, you can leave. If you do, you can stay on and ask.